Okay, welcome to your bonus lecture. I asked you a while back what sort of things would you like to know a little more about, and spatial analysis came pretty high on the list. It wasn't everyone's choice, but there were more people that chose this than any other option. So what we're going to do here is just cover a few more types of spatial analysis that we can do in R. And just remember that even though this was a sort of a bonus lecture, it's still going to be on the final exam, so pay attention. All right, so what we're going to do here is we're going to talk about hotspots, spatial autocorrelation, and web scraping, and all this is going to be powered by ChatGPT. So what are we going to cover? Well, we're going to cover hotspot analysis. We're going to cover measuring spatial autocorrelation, basically global Moran's eye. Hotspot analysis, Geddes, Ord, GI star, and then we'll do some real simple web scraping. And we're going to do all this stuff in R. We'll start off with the hotspot analysis. This is kind of a redundant slide. I should have probably taken it out. All right, so quick review on hotspots. When we talk about hotspots in ArcGIS anyway, we're generally talking about the Geddes Ord GI star. That's how it's pronounced, GI star test. And a hotspot is a high value that's surrounded by other high values. The way it does this is it's actually kind of interesting. It basically looks at a neighborhood or an area and says, okay, what is sort of our average value here? And it does a neighborhood or area for each point. So say you got 2 points that are relatively close together. You might have almost completely the same neighborhood. Either way, it's going to look at those surrounding values and say, okay, what are they? And it calculates all the stuff, the mean, standard deviation, etc. Also does the same kind of thing for the entire data set. What it then does is it compares the value at that local area around each spot to the global overall data set and converts all this stuff into z-scores so that you can see just how close to the same they are or how different. And then from z-scores you can then calculate p-values. There's a new tool called the Optimized Hotspot Analysis tool, and it does the same calculations, but it looks at your data and it optimizes the settings to get the best possible results. So it looks at the number of samples in your data set. It looks at variance and things like that, and it goes through all these different things and says, okay, given this, this, and this, what should the settings be where there are settings that we can change. Things like search radiuses, the number of neighbors, that kind of stuff, or what have you. It'll then optimize that. Now what we're going to do is we're going to look at running just a basic Geddes Ord GI star in R. We're going to use the data set that's pre-installed in R called Quakes. All right, so looks kind of like this. And so what I did was I went through for each of these three topics, and I developed a script that will do the thing that we want to do in R. I then took that script back into Chat after I had finished and broke it down into sections and allowed it to explain in simple terms every function or variable input in each line of the script. And then I copied those outputs onto the slides here that I'm going to show you as we walk through it and as I talk about it. Now, I have given you these scripts in R. I would prefer you work through using what you see on the screen, what you get in the lecture notes, and try to reproduce this on your own with assistance from chat before you dig into opening up the code I shared. And then hopefully that will help it make sense. So let's get started. Load the Quakes data set. That's pretty simple. It's just data, and the data we're going to look at is called Quakes. And then I wanted to go through and clean the data because I wasn't sure if Quakes was a cleaned data set. And so we're going to call it Quakes 2. And basically, we're going to use the NA-omit function on the Quakes data set. And so what does that do? Well, that looks at that original data set Quakes. Anywhere there's a line with an NA, it omits that sort of row. And that's how you clean data. One way. And then I wanted to display the number of entries in the clean data set. And so we use that next bit of code. And so what does this do? Well, the cat function concatenates the output and outputs the arguments provided. It's used here to format a print message to the console. The number of entries in Quakes 2 clean data set. This is a string that describes basically what's being printed, indicates that the number being displayed refers to the clean data set Quakes 2. In row Quakes 2, this function counts the number of rows, and that basically gives you the total number of observations. And it should not have any missing values after the cleaning process. And then you have that quote \n. This is a new line character that moves the cursor to the next line in the console after printing the message, making the output cleaner and easier to read. That's all. So started off here, a lot of times with packages, when you go to install something that's already installed, here I wanted to just show you a quick way, maybe not so much a quick way, but a way that you could structure how you install packages so that it basically checks to see if the package is installed, and if it's not, it then installs the package. And that's basically the code that we have here. And we're looking for the SF package, and then we run the library of that. And then the next line of code is going to convert the clean data set Quakes 2 into a spatial object. And then we transform that object from the coordinate system that it was in, which was a GCS, into the appropriate projected coordinate system. And this data set happens to be in Fiji, which turns out, excuse me, is UTM zone 60 south, I think, yeah. And then we put a head function in there to display the first couple rows of it so that we can see what it looks like. So let's go over here and look at the explanations here a little bit. So you've got the whole if line function there, and we start on the inside where we have the installed packages. Installed packages basically returns a list of all the currently installed packages. The SF with the percent in front of it is just a way of going through that list of installed packages to see, hey, is that here? And so that's what the install packages with the SF in quotes is doing. It goes through that, If it's not installed, then it kicks out to the end to the uh, brackets, and the brackets, of course, then tell you um, to install the package, and of course the package is in the parentheses inside the brackets, which is SF. And then the last thing is the library function for SF, which loads the SF package into R, making it everything available to use. Convert to spatial object was the next sort of step, and this is the one where we take the data set and we make it a spatial object. So we're going to call it then Quakes SF. And so what is Quakes SF? Well, it's this st_as_sf, which is a function that converts whatever data set we tell it, in this case Quakes 2, into a spatial object. And then explains that the coordinates are, and it gives us the longitude and latitude, and which specify the columns that they use for those. And then the CRS, the coordinate number of 4326, which is basically the WGS 84 GCS coordinate setup. The next step was to then convert that into a UTM or some other projected coordinate system, because we never ever do any kind of spatial analysis on data that's in a GCS. And so we are going to then take that Quakes SF, which is what we had converted there before, and we used the ST transform on that data set to basically change the CRS, the coordinate system number, to 32760. The ST transform changes it to a spatial object, just like we, but it changes it to the one in the one that we want. And then of course we did the head function to do the first couple rows in the display. Next, there was another package we needed that was the SP deep. Again, I used that same setup where we used that long function where installed packages returns a matrix of what's currently installed, and then the SP deep with the link to install packages, it checks if that package is in the list. The exclamation point operator negates the check, meaning if it evaluates to being true, if stdep is not installed. And if it's not installed, then it goes and kicks out to the brackets where it has install packages, spdep. And then of course the library, because once you install it, or if it's already installed, we then just call out the library to load it up into R. All right, next we're going to extract the coordinates from the spatial objects. We're going to create a nearest neighbor using 20 nearest neighbors. We're going to convert the neighbors to a list. We're going to create a spatial weight from the list, and we're going to summarize the characteristics of the weights list. So let's look at that a little bit over here. Coords 3, it just uses the ST coordinates function on the Quakes SF dataset, and that extracts the coordinate matrix from the spatial object. Next is to find the nearest neighbors. Neighbors 20 is what we're going to call it. We use the knear function, and we do it on the coordinates 3, the coordinates that we extracted. And k is our number, and it's going to be 20. So the knear function identifies the nearest neighbors. we put in 20 is what we wanted, so it's going to do that. It then creates this neighbors list, converts the output, which then allows us to create spatial weights. And yeah, that allows us the first step in the process. And that process is calculating the get-us-ord GI star statistic and p-values. And so GI star is what we're going to call it, and it's just basically just the local G, which the local G is a function that calculates that statistic. Some of the input parameters is we have to tell it what variable you want to do this on, and so we wanted to use the Quakes 2 data set, and we wanted to use the magnitude variable. Again, use the weights data set that we had created earlier. So what we used there. The next step is to add the GI values to the data set. So that's where the Quakes _SF $GI _star is what we're calling it. And basically what this does is it adds the calculated GI star values to the spatial object, creating this new column called GI star. And then there's the p-values. Again, the p-norm function calculates the distribution function for a normal distribution, uses that to turn the p-values off of the GI statistic. The ABS Quakes _SF $GI _star takes the absolute value of the GI statistic to assess significance. It multiplies p-value by 2 according to a two-tailed test to make sure that it takes care of that, and so forth. Hotspots are something you need to map, so we had to load in the tmap. Again, use the same sort of syntax I've been using to see if tmap is installed, and if it's not installed, to then install it, and then calling up the library for tmap. In this scenario, we made one map with z-scores, and we made one map with p-values. Almost identical bits of script, except one's for map 1, one's for map 2, and in terms of what we're actually looking at, what's our variable, most of the other stuff remains pretty much the same. And lastly, we want to display the maps side by side, so we're going to arrange map 1, map 2 in 2 columns. On the right, you see a little bit more detailed breakdown of what some of those inputs are, like, for example, the style is set to pretty, which applies a classification style to GI star values for better visualization. The 0.3 is the size. Alrighty, let's see. So, want to know what that looks like? There you go. There are all the earthquakes in and around Fiji, and you can see there are z-scores and p-values associated with those individual earthquakes. Now, about halfway through the script, when you're tinkering with it, you will get a warning message about the points being identical, and that technically could be a real problem. We didn't address it in this calculation because we're going to address it in the next one. So let's take a look at what we're doing next. Well, first let's talk about how we're going to fix it, and then we'll look at it. You could redo the analysis on a distance basis and not use the number of closest neighbors, but just say everybody within, a mile or 50 miles or 20 miles. There's also something called jittering the points you can do using the ST jitter function. It adds a slight amount of noise to the location so that the points don't overlap. That's an interesting way of looking at it. So how are we going to measure spatial autocorrelation? We're going to do it with a global Moran's eye. We're going to use the same data, same basic kind of strip that we had for the first part, and we'll move forward from that. So just like before, loaded up the quakes data, cleaned it, cataloged it, printed the head. That's pretty much the same. I'm not going to go back over that. Again, same kind of function. Checking to see if SF is installed. If it's not installed, installing it. And then the last line, creating this new data set called Quakes_SF, which basically looked at the Quakes2 data set and made sure that it had coordinates and they were in the proper GCS. Next, we reprojected them into zone 60 south, just like before, same code. And then we had two packages to load, the SP and the SP dep, which we did, and then called in the libraries for each of those. And here you get a breakdown of how that works if you want to read those. Which gets us to our Moran's eye test, which has got a lot of weird steps. First, you have to set the seed, and then you got to create your stuff, print ahead, do some things to figure out your weights, ultimately get your results. So we ran that script, and now we'll look at those 9 points just a little bit. Set seed ensures that the random number generator is reproducible. Using the same seed value will yield the same results each time the code is run. That can be helpful. All right. Had to take a momentary pause there. We've done the set seed. Next is applying the jitter. So we basically called the new earthquakes jitter quakes. We use the ST jitter function, which is the most simplest one, and it just basically takes your earthquakes that are in UTM and applies a certain amount of jitter. And in this case, we gave it a 0.1 in terms of meters, which is a 10 centimeter. That small amount will help make sure that they're not directly over top of each other. We set up the head for jitterquakes to display the first 6 rows. We extracted the coordinates. We found the neighbors. We can convert to a neighbors list. Again, taking a little pause there just to get my thoughts straightened around here before we continue. This is going to be a relatively long slide, I can tell. Once we have the nearest neighbors, we convert the list and create the weights. We can then calculate the global Moran's eye. And it's just simple Moran test function. Ran on that Jitterquakes data set that we made. And it looks for spatial autocorrelation. And then we told it to print the results, and you get this. Just wanted to briefly talk about the p-value. So Moran's eye tests against the null hypothesis. So this is the probability that you got these values and that you got them just randomly and that there is no spatial autocorrelation. And the probability of no spatial autocorrelation is extremely, extremely tiny. That means that the probability of I'm having a hard time explaining what I want to explain with this p-value thing. Give me a second here. All right, let's try this a different way. All right, so when you're hypothesis testing, say you set your threshold at 0.05. At 0.05 p-value, that means at 95% certain there's an interaction, and 0.05 or less % certain that there is not. And so what we're testing for here is spatial autocorrelation. And so p-value is of the null hypothesis, that there is no spatial autocorrelation. So the smaller that number is, that means the larger the chances that there is spatial autocorrelation. And this is 15 zeros followed by a 2. That's how small the chance is. So this data set is extremely spatially autocorrelated. Well, I hope that was worth it in the end, because that was a struggle to figure out how to get that out. All right, web scraping. I've done a little bit of this in the past. I'd never done it in R until today. It's a challenging thing to demonstrate because you have to have a reason or a rationale or a cause to do it. And that's not always easy to come up with. There are some free programs out there to do web scraping. There's also a lot of issues potentially about it, like some websites don't want to be scraped. So you need to look at the terms of service on a website and make sure it's okay to scrape it, and that you're not in violation of someone's intellectual property by doing so. So we're going to look at formatting a script to grab some information from a website. In order to do this, we're going to have a couple of different packages installed maybe. So what we're going to do is, because I don't have any of these installed already, I don't have to go through that check process to see if it's installed, and if it's not installed to install it. I know these aren't installed, so I'm just going to install them. Makes the script a little easier to read too. Install packages, and then of course there's the list of the ones that we're going to install, and so that it works its way through it, installs all of them, and then right after that I have the 3 library functions for each of those packages to then load those up. The next is you have to define the URL that you're going to scrape. In this case, I'm looking at a URL called Books to Scrape. This is a particular website that welcomes people who want to web scrape their website. So the purpose is to set it so we know where we're going to and what we're going to do. And then we're going to read the HTML from the website. So web page, read HTML, URL. We already defined the URL. And it's going to fetch the HTML content from the specified URL. function of the RVS package that retrieves the HTML and stores it in a variable called web page. This variable now contains the entire HTML structure of the web page, and we can parse that around to extract certain things. One such thing is the book titles. So we're going to say titles is web page piped to the HTML nodes, quote, dot product underscore pod h3a, another pipe connector to HTML attr title. And what are we going to do with this? We're going to use this CSS selector to find all anchor elements within the hashtags inside the elements with the class product pod that has books titles. The HTML attr title reviews the values of the title attribute from the selected nodes, resulting in a vector of book titles which is stored as the titles variable. Now, I'm not going to go over this verbatim just like we did before. It's basically the same thing, but now instead of title we're looking at prices. And then there's one called availability, looking to see if something is in stock or not in stock. And lastly, we're going to look at extracting the ratings. So there's a star ranking on this website of like maybe 3 stars or 4 stars or whatever, or 2 stars or 1 stars. This will, from HTML, basically count the number of stars and then add that into your result. Once you have that all done, you got to combine it into a data frame. So we're going to call it books data frame, and it's going to be equal to the titles, the prices, and the availability and the ratings. We're also going to view the first few rows of the data with the head function and see what that extracted data looks like. So I wanted to show you what the web page itself looked like. So this is books to scrape. It says we love being scraped. And there's the HTML, HTTPS address at the top. And you can see that for each book, like for example, A Light in the Attic, there's a star rating, 3 out of 5. There's a price, and it tells you whether or not it's in stock. It would be your availability. What the web scraper does is it goes through all that HTML code and it converts all these things that you see on this web page into a database. And here, in the black box on the left, you can see what that would look like. Yeah, so yeah, that's basically it. It's going to go through the website, it's going to record that information, it's going to put it into the database. So that's it. That's hotspots, spatial autocorrelation, and web scraping as powered by ChatGPT.